My name is Daniel Merson. Welcome to Lab 4 Circuits. In this lab, the purpose was to predict the behavior of circuits containing resistors and capacitors in series and parallel. We had to use multimeters to measure the actual values of conventional current and potential differences in the circuits, and we had to examine the behavior of ohmic resistors and capacitors. The fundamentals at play here are the conservation of energy and charge, Kirchhoff's laws, which are the loop and node rule, which you can see in the middle right, where for the round trip potential difference, it always is going to be equal to 0, and any current going in and out of a node has to be equal to each other. We have to talk about steady state circuits, which we'll be talking about later. Ohm's law, which is V equals IR. Capacitance of a capacitor, which is C equals Q over V. The difference between series and parallel circuits, and the implications of time in RC circuits. For the model, I use the online PHYS circuit simulation to conduct the experiment, and just as a little preview, in each section of the experiment, the results match those expected by the formulas used at the lab. And our experimental RC ended up being about 5.99 seconds. Our assumptions that we have to make are that there is zero resistance in wires, that is negligible, and this is stated in the PHYS simulator, and that there's also zero resistance in the ammeter. Together, these make sure that Kirchhoff's loop rule only takes into account the components of the circuit. Our initial conditions vary according to the section of the experiment, where either the capacitor is charged or discharged, but T is always equal to 0. Our system is the circuit, and everything else is the surroundings. In part 1 of the experiment, we have two 1.5 volt batteries, two resistors, 47 and 100 ohms each, two emitters, and a voltmeter. The model is depicted up and to the right, where you can see the thing that we modeled in the PHYS simulator. And our prediction, using the node rule and Ohm's law, we can see that we predict it to be the current in the circuit to be 0.02 amps. And when we actually look at the ammeter, this confirms our guess, where it actually reads 0.02 amps, and this will be negative if the ammeter was reversed. If we replace the ammeter with a voltmeter, there's going to be no current and the voltage is going to read 3 volts. This is because when there's no completed circuit, current cannot flow. And with an open circuit, the potential difference between the gap still is going to equal the potential difference of the source, which in this case is the batteries. Going on, we can see that when we measure between these different parts, the potential differences in the circuit, we can see that still Kirchhoff's loop rule holds, which is as expected, where 3 volts minus 0.96 minus 2.04 volts is still going to be equal to 0 volts, so the loop rule holds. And still just checking, the current through the circuit is 0.02 amps, and this is because the potential difference across an ammeter is not affected because of the negligible resistance in the ammeter. Looking at the graph, we can see that where there is a flat slope, that's where the wires or emitters are because there's no resistance. There's a positive slope where potential increases, this is the batteries, and there's negative slope where the resistors are. So in the first one, the 47 ohm resistor, we go down about 0.96 volts, and for the second resistor, we go the remaining 2.04 volts. We can see here that when we run in parallel a resistor and an ammeter, we can see that the current is going to be passing through the ammeter, and we get a different answer for the different reading for the current passing through the circuit, and this allows us to find the actual resistance of a couple of the resistors and components on the circuit, where the 47 ohm resistor is actually 48, and the 100 ohm resistor is actually 102. For the next part, we have to talk about what we're using. So we got the 10 ohm bulb, the 20 ohm bulb, the 9 volt battery, and a 200 mF capacitor, stopwatch, and a voltmeter. So when we're charging the capacitors, regardless of the bulb we were using, when the capacitor was charging, voltage was rising and the bulb continuously dimmed because the current was going down to 0 amps. When we were discharging the capacitor, regardless of the bulb, when the capacitor was discharging, voltage dropped and the bulb continuously dimmed. Again, the current was going towards 0 amps. For the 10 ohm bulb, it took 15.4 seconds to charge and 15.3 seconds to discharge. And for the 20 ohm bulb, it took both 27.6 seconds to charge and discharge. For the next part, we have a 30 ohm bulb, a 9 volt battery, 200 mF capacitor, stopwatch, and a voltmeter. You can see the data that we collected over a 20-second interval while charging the capacitor, and you can see while we were plotting this, we can see that the slope of the line that we got, negative 0.167, allows us to use the relationship found in the instructions to find an RC of 5.9 seconds, which means that our theoretical RC of resistance times capacitance of 6 seconds has a percent error of 0.167, which is essentially negligible, meaning that I humanly made a mistake in one of the points when collecting data. So what if we were doing this lab in real life and we were using an actual emitter instead of an ideal simulated emitter? The difference would be that in real life, the actual emitter would have some resistance, so it would likely change the current output, making it lower than in the simulation. What if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? And how quickly would our ideal model predict the capacitor to reach fully charged? We should expect this to be done immediately, but because there's always going to be resistance on the wires, that is never going to be the case. When we look at the conclusions, as capacitors are charged or discharged, the current in a circuit decreases with time until steady state, and currents alongside voltages differ according to Kirchhoff's node and loop rules and are also time dependent following a differential equation.